Hey everybody, I want to talk to you about a little bit of a technical topic today, which is how to combine normal distributions. It turns out that we're going to need to do this, sort of. So we need to do this to combine or to do two sample hypothesis testing. So when I say sort of, what I mean is normal distributions need to be combined for us to do two sample hypothesis testing. We're not going to have to do it manually by hand. We're mostly just going to hit the two sample test button on the calculator, but I do want to explain how it all works. So this one's going to be a little bit messy, and I've got a lot of data to show you as an example. But yeah, so that's where we're going with this. I'm gonna show you the motivation for formulas and techniques that we're not actually going to use in practice, because I don't want to get in the habit of thinking of the calculator or the computer as like a magic answer box where you do stuff but you don't understand what you're doing and you get a number and you interpret that and you know don't really know what that number means. So I'm going to show you where it all comes from, and when this all gets a little bit messy, don't worry too much. I'm not going to make you do too much of it by hand. There's like one or two questions on the homework, but yeah, anyway, let's go. You'll see what I mean. So I want to show you how to combine normal distributions. And when I say combine, what I mean is subtract. So here's the idea. So eventually we're going to want to conduct hypothesis tests that compare one sample to another sample, right? Up until now, we've been comparing one sample to some fixed number, which is a fine thing to do. It's a thing that comes up perfectly reasonably often. But it's often the case that what you want to do is compare one sample to another sample. And since there's uncertainty in both of them, which is to say they both come from some distribution, what you want to find is the distribution of all the differences of everything in one and the other. And I'll explain what I mean in just a second, but because that's a little bit complicated. So here's the basic formula. So if A, oh, and by the way, pardon the handwriting. I'm sorry, Zoom will not let me type Greek letters, so we're stuck with handwriting. So if A is a normal distribution with a mean of mu sub A and a standard deviation of sigma sub A, B is a normal distribution with sigma sub B, or with a mean of mu sub B and a standard deviation of sigma sub B, then A minus B, I'll explain what that means in just a second, is a normal distribution with a mean of mu A minus mu B, so you just subtract the means like you'd expect, basically. And then the standard deviation is this thing, which is probably not what you would expect, but I'll explain why it is this. So it's the square root of sigma A squared plus sigma B squared. And yes, that's supposed to be a plus, it's not a minus. And I'll show you why in just a second. So I've got a bunch of data I want to show you. But before I do that, I want to explain what A minus B is. So A minus B here is another distribution. And it is the distribution of everything in A minus everything in B. And what that means is not you take A1 and then you subtract off B1. You take A2 and you subtract off B2. You take A3 and subtract off B3. No. What it means is you take A1 and you subtract off B1, and then A1 and subtract off B2, and A1 and B3. And once you've gotten through all the B's, then you go on to A2 and you do all the B's. So there's way, way more stuff in A minus B than there is in A or B. In fact, you multiply the number of elements in each one to get the elements in this one. Now, since the normal distribution actually has an infinite number of things in it, you just get infinity again. So in the infinite case, that's not true. Or I don't want to say that's not true. It's still true, but the number you get isn't actually any larger. So the thing that I want to show you is I have made an approximation of A, B, and A minus B in sheets. It's a bit of a mess. Where's my thing? I literally just finished making this. What? Oh, sorry. I switched tabs and didn't realize it's this one. Okay. All right. Little snafus aside, let's see how this works. So I've got B and C here are data that I generated randomly. I just use the random function. You can't see it right now because I had to take out the formatting so it wouldn't keep changing the numbers on me. But just rest assured that what I did in column B was I have randomly generated data from the normal distribution with a mean of 10 and a standard deviation of 5, right? So since it's random data, those things aren't exactly the same here as the sample mean and standard deviation, but that's the population they came from. And in column C, I have a normal distribution, or I've randomly generated data from a normal distribution with a mean of 5 and a standard deviation of 5. So this had the population here had a mean of 10, population here had a standard deviation of 5, mean of 5, standard deviation of 5. You can kind of see that in the histograms. So I made histograms of both of them. You can see they're both roughly normal because it's random data. Of course, it's not going to be perfectly normal. But B goes roughly from -3 to about 20 and is centered at, it should be centered around 10. This is slightly lower than that. The average here was 9.4. So centered right around 10. That's the idea. This one was centered right around 5. Right, the average actually turned out to be slightly lower than that as well. And then what I did was I made B minus C. So I took this one thing and I subtracted off everything in this column. And that's what column E is. So like you can see, I don't know if you can tell here, but this says B1 minus C1. And don't worry about the dollar signs, like just ignore those. This is B1 minus C2. B1 minus C3. So in other words, it's this thing minus that, and then this thing minus that, and this thing minus that, etc. And that's what column E is. It's B1 minus everything in column C. And then F is B2 minus everything in column C, and so on and so forth, right? This is B6 minus everything in column C. That's what column J is, right? You can see that it's the sixth one minus everything in column C. And so I've made, so there are 25 things in column B and C, right? 25 data points in B and 25 in C. So that means we have 625 things in B minus C, right? So it's all these. And don't worry about this last column. That's me putting them all in one column so I can make a histogram out of them. That was a pain in the neck. But that's what all of these numbers are, that is the distribution B minus C basically. And I made a histogram of that too. And so here it is, right? It's much bigger. It's got a lot more data in it. But the thing I really want to point out more than anything else is that the mean is roughly where you'd expect. So if this is centered at 10 and this one's centered at 5, when you subtract B minus C, you would expect it to be centered around 5, and you can see it is, right? There's the middle. I know it's a short one, but the middle is around 5. In fact, we can find the mean and standard deviation of those, right? So the mean goes here. We'll do equals average of E1 through, I believe, AC25. Let me make sure I got that column right. Yeah, it was. And so there is the average, right? That's the average of everything in there. Now, let me point something out. So the average of these two things, so this is in B27 and C27. If I take B27 minus C27, I'll get exactly the same thing, right? So these are exactly the same because you can, the average of the differences, right, which is what this is the same thing as the difference of the averages. That's not quite true for standard deviation. If you remember, I claimed that the standard deviation was this thing, the square root of sigma A squared plus sigma B squared. And that's not going to come out exactly the same in our example because this calculation relies on the smoothness of the normal curve, which we don't actually have, right? But we just have something approximating it, but it'll be pretty close. So let's see what it is. I haven't actually calculated it yet. So the standard deviation, so if I do dV of, oops, I forgot the equal sign, equals dV of E1 through AC25, right? So the overall standard deviation, notice that's higher than either of these individual ones, right? These individual ones, the population standard deviations were 5, but these guys were 5.7 and 5.5. And then when I subtracted them and got the differences, the standard deviation turns out to be bigger. And I'll explain that in just a second, but it is. And I want to compare that to equals square root of, oh shoot, I forgot that it was B28 and C28. All right, square root of B28 squared plus C28 squared. This should be similar, but not exactly the same. Yeah, so there you go. So it's a little bit, it's about the same thing. If this was actually the population, those things would be equal, right? This squared plus this squared would be actually equal to this, or which is to say this and this would be the same thing if this was actually smooth normal curves. Since it's random data, you get something approximating but not exactly the same. So let me explain why the standard deviation goes up when you subtract things. It's also true, by the way, if you add them, you get the same exact thing with the standard deviation. So here's why. So I'm going to pick a couple of choices for B. So B here, the third element in column B is 19.3, and then the 10th one is negative 2.74. So when I take this and I subtract, let's say E here, or E1 here. No, that's not what I'm subtracting. Let's try it again. I subtract this negative number, right? So when I do 19.3 minus 7.86, the thing I get is bigger, right? Because minus a negative is a plus. So the thing I get there is like 27, which is bigger than anything in either column. And when I do like negative 2.7 minus 11, the thing that I get is negative 13, which is smaller than anything in either column. So what I get is this stuff with a larger range, because like you can see down here, right? So this goes from like, what I say, 3 to 19. So it's got a range of about 22. This goes from like negative 8 down up to 17. So it's got a range of about 25. And when we look at this thing, it goes from negative 20 up to 30-ish. So it's got a range of about 50. And that's because when I take something that's over here and I subtract off something that's over here, so the biggest thing in B minus the smallest thing in C, that gives me something that's bigger than is in either column. Similarly, when I take the smallest thing in B and subtract off the largest thing in C, I get something that's much more negative than anything in either column. So that's why I get this increased range. And that's why you get increased standard deviation as well, because the larger range of data gives you, it's just more spread out, right? And so that's what happens if you subtract. You can make this exact same argument for addition. We're not going to be doing the adding, but just heads up, you can. So when I say B minus C, or I guess A minus B on the whiteboard, but when I say B minus C, what I mean is everything in B minus everything in C in all possible combinations, which is a lot of stuff. So this distribution of this combined distribution is much bigger than either one. And in fact, it's much bigger than the two of them just like stuck together in one distribution, because you have to do every single combination, of which there are many, right? I kind of wish I hadn't done 25 and 25, because I have to tell you, this column of 625 numbers took a while to make. You can see that there's a lot more in this column than there is in either of the other two, right? And a lot more than just if you added the two of them together. So anyway, that is what I mean when I say A minus B. Let me go back to the whiteboard and show you what we're going to do with this. So here's the idea. Well, I'm gonna demonstrate the idea with an example, I guess. So here's my example. I'm going to let M be the distribution of American men's heights, and W, I don't know if you can see that, W be the distribution of American women's heights. According to the CDC, men's heights are approximately normally distributed with a mean of 69.5 and a standard deviation of 2.5. And American women's heights are approximately normally distributed with a mean of 64.3 and a standard deviation of 2.4. So here's what we're going to do with this. I'm going to find the distribution I'm going to find the distribution M minus W, but I want to talk about what that is. So here's sort of what that distribution means. It is all the pairwise differences in height between men and women in the United States, or I should say, pairwise differences is okay, but it's how much taller the man is than the woman in every pair, right? So mostly that'll be positive. Sometimes it'll be negative, right? Because sometimes you'll get a pair where you have a short man and a tall woman and the woman's taller. So M minus W is all possible combinations. Like picture You take all 100-ish million men in the US, you put them in a big room. You take all 100-ish million women, and you put them in a big room, and you say, okay, man number one, come on out. Woman number one, come on out. And you find out how much taller the man is than the woman. Then you send the woman back, and you bring out woman number two. And you compare man number one to woman number two. You send the woman back, bring out woman number three, compare man number one to woman number three. You do this for a long time until you get all the possible combinations. That's what this is, the distribution of all the possible combinations of differences in height, man's height minus woman's height, which is to say how much taller the man is than the woman. So I want to find this, find m minus w. So let's go over here and do this in blue. Let's do it in blue. I like blue. So I'm not going to write down what I just explained for m minus w. I'm just going to talk it out. So I'm going to say that m minus w is approximately normal. The mean of, what do I want to say here? I want to call it mu sub m minus u sub w. And I'm just using subscripts, of course, to identify which mean I'm talking about. And a standard deviation of sigma m squared plus sigma w squared. All right, and that equal to n. So this was 69.5 minus 64.3, I believe. I will calculate that in a second. A standard deviation of square root of 2.5 squared plus 2.4. 4 or 3, I don't remember. I'm gonna look this up. 2.4. Okay. 4 squared. Which is going to be bigger than the standard deviation of either one, just like we saw in the example. So let's finish this. This is going to be n. And so the difference there is what, 5.2 inches? 5.2. And that is a thing that I'm going to have to go calculate. Where is my calculator? Calculator. All right, so we've got square root of 2.5 squared plus 2.4 squared. That gives me 3.466, we'll call it. 3.466, which is of course bigger than either one. Okay, great. So this new distribution, notice that it's centered much lower than either one because we're finding the differences of all of them, right? And so the differences of all of them are differences between 69.5 and 64.3 is much smaller than either one. So this is centered around the mean difference and a little bit more spread out than either one started out to be. Okay, let's see what B says. Let D equal m minus w. So I just to be explicit here, I'm using capital letters to mean names of distributions. So this is the name of a distribution. This is the name of a distribution. And I'm thinking of, I actually probably should have put parentheses around this, but this right here is one distribution, right? I probably should have written it like, like this. Because that's, I want you to think of that as one thing. It's one thing with a lot of, it's one distribution with a lot of things in it, but it's just one distribution. So this guy right here, D equals m minus w, this is little d, stand for difference, and then little m and little w. So this is one man's height. That's one randomly selected man's height. And w is one randomly selected woman's height, which you can think of. You can think of this whole, like this thing as collectively one number. And it's one number that's in this distribution, right? Because this is all the possible differences in heights, and this is one of them. So that's in that distribution. And I think I got to undo a lot of stuff. I'm just going to call that thing D, just so I don't have to write m minus w for everything and can just use one letter for it. So this is my letter for that. I'm going to let D be a randomly selected point in m minus w, right? So it's one difference between one random man and one random woman. And I want to find the probability that D is bigger than 6. So in other words, what's the probability? Oh, I'm sorry, I meant to make that 7. I'm gonna change that. I've got a chance here before we go any farther. I'm going to make that 7. And the reason I'm making it 7 is because that's what I did later too. my later one is also 7. So I'm going to find the probability that the difference is greater than 7. So this is the probability that if I pick a random man and a random woman, random American man, I should say, random American woman, that the man is at least 7 inches taller than the woman, or more than 7, I guess the way I've written it. So this is the probability that if I pick a random man and a random woman independently of each other, that the man is more than 7 inches taller than the woman. Now, this is actually pretty easy to do because I have the distribution of all the differences, right? This is not particularly hard. We've done this a million times. This right here is this is the distribution of all the differences. So all I'm doing is I'm saying, okay, given that M minus W, this thing I should put in parentheses, is that distribution, find the probability that one thing in that distribution is more than 7. Well, that's easy, right? So this is normal CDF of 7 to infinity with a mean of 5.2 and a standard deviation of 3.466. Right? Easy enough, not much to it. Let's go calculator it up. Calculator. So we're going to do normal CDF, distributions, normal CDF for 7 to infinity, just something really big, with a mean of 5.2 and a standard deviation of 3.466. 30%, which sounds about right? If the average man is about 5 inches taller, a little more than 5 inches taller than the average woman, then, some of the time the man will be 7 inches taller, right? About 30% of the time, like it'll happen relatively frequently. So, yeah, let's go write that down, 30.2%. About equal to 30.2%. All right, now luckily I've left myself another blank page because I got one more question to answer here. Whoop, go back. Okay, find the probability that if we select a random American man and a random woman and a random American man, that the woman is taller than the man. So that, I've asked this question a bunch of times when I used to teach in a classroom. And that question always stumps my students. Not always stumps them, but it's a trickier question to get. So what I want to do is I want to graph the distribution of M minus W. Right, so here's my distribution. It's normally distributed. Its mean is 5.2. This is N5. That's not grade 5. Let's try it again. 5.2. Good enough. 3.466 is this. And let's do this. Man taller. Man taller. Woman taller. Or I guess less short. Less shorter is probably not the appropriate way to say that, but that's kind of what it means, right? So here's the idea. So as we go further to the right, the difference between the man and the woman's height becomes bigger, right? So if we had a 7, right? So here's 7. And so I know that this area right here is the thing I just found, right? So this is, and at least, so that area right there is where the man is at least 7 inches taller than the woman is. Okay, so the place I can find where the woman is taller than the man is when the difference becomes negative, which is at 0, right? So over here, wherever this is probably farther to the left, but whatever. So this is 0 here. And over here, the woman is taller than the man. Oh, I guess I'm gendering that color by making it pink. I'm switching it. I'm not going to be accused of any nonsense here. So there we go. Okay. So over there is where the woman is taller than the man, because anything to the left of 0 is negative. So over here, this is where the woman is taller. So I just need to find the the probability, so asking where the woman is, what's the probability that the woman is taller than the man, is the same thing as asking what is the probability that D is negative. Okay? That's the woman being taller than the man. So of course we use normal CDF, and I'll go do that. So we're going minus infinity up to 0 here. So where are we at? Calculator. All right, so normal CDF minus infinity, so minus a lot up to 0 with the same mean and standard deviation, and we get 0.0667. So about 7% of the time, which sounds about right. Right? It's not super common that if you pick a random woman and a random man, that the woman will be taller. It's not super uncommon, right? It happens some of the time. So yeah, so I'm going to call this 6.7%. Oh, I'm being sloppy about what color I'm using here. Sorry. About equal to 6.7%. So this is how we combine normal distributions. When I say combine, I really mean subtract. We're never going to do anything else but subtract them. So yeah, this is how we get the distribution of all possible differences between two normal distributions. So let me see where we're going with this. So I'm going to expand on that a little bit, because here's what we actually want to do. We want to combine not just any normal distributions, but specifically sampling distributions. And I think my picture's in the way here, but specifically sampling distributions. Right now, the central limit theorem guarantees that most of our sampling distributions are normal, or at least most of the ones we're going to be using turn out to be normal. Right? If we take a large enough sample size, the sampling distribution of the sample mean is approximately normal, and the sampling distribution of the sample proportion is also approximately normal. And we're going to use both of those when we do hypothesis tests and make confidence intervals that are coming up in the next videos in this module. So that's what we're going to do. So I want to build on the same thing here. I want to build up to that here. So what I'm going to do is I'm going to think of, instead of taking one man and one woman and comparing their heights, I'm going to take a sample of 20 men and 10 women. And the sample of 20 men, I'm going to find their average height. Sample of 10 women, I'm going to find their average height, and then we're going to compare those averages. Now, I should say, you might be wondering why fewer women. I'm only doing that to show you that you can use any sample size, that the sample size doesn't actually matter, and it's fine for them to be different. In actual practice, if you were doing anything like this, you'd use the same sample size, because it does alter the results just slightly, but not enough that we're going to worry about it too much. But yeah, so I'm only using 20 and 10 to demonstrate that it's fine if you use different numbers, or it's fine if you use different sample sizes, that works okay. So I want to find the sampling distributions X bar M and X bar W, which are just what you think. This is the sampling distribution of the sample mean for men, and this is the sampling distribution of the sample mean for women, right? That's why capital X bar. I know it kind of looks like a little lowercase x bar, but I swear that's capital. So let's do that. Let's go over here and say that the sampling distribution of capital X bar sub M is approximately, we know from the central limit theorem that it's normally distributed. Now, I should say, a lot of people get hung up on us using sample size, a sample size of at least 30 for this. We don't need that in this case, because the population is normally distributed. Remember that we either need a large sample or a normally, that is not what I wanted to have happen. Let's try that again. Oh, okay, good. We either need a large sample or a normally distributed population. We don't have a large enough sample, but that's fine, because we have a normally distributed population, so we don't need it. So yeah, I'm gonna go back over here. All right, so sampling distribution XM bar or X bar M and X bar W. So X bar M is approximately normally distributed with a mean of the mean of the population, which is 69.5, so mu sub M, and a standard deviation of the standard deviation of the population divided by the square root of the sample size, which is 2.5 divided by the square root of 20. We'll find that number in just a second, or maybe I won't even bother. Do I want to bother? Yeah, we'll see. So X bar sub W, same thing with the women, right? Approximately normally distributed, mean of 64.3 and a standard deviation of 2.4 over the square root of 10. right? Yeah, I'll go ahead and find decimal approximations for those things. Why not, right? So this is n 69.5 comma something that we'll find out, and this is n 64.3 comma something that we'll find out. All right, so let's go. Let me move my picture out of the way because it's, as always, going to be right in the way. Let's go to the calculator. 2.5 over root 20, 2.4 over root 10. So we're going to go 2.5 divided by the square root of 20 and 2.4 divided by the square root of 10. All right, so 0.5, let's say 0.56 and 0.76. Sure, we're rounding off a little roughly here, but that's fine. 0.56, 0.56, 0.76. Or rather, I should say, I'm not worried about the rounding in this case because I'm really just trying to demonstrate how this stuff works rather than worrying about getting the absolute utmost precision. You should probably go a couple more decimal places than that. I'm just doing it for convenience here. All right, those are the sampling distributions. Fantastic. Find the distribution of differences of sample means. That is, there's a lot of information in there. So what I want to do is, what I'm really trying to say here is, well, this is the difference of the sample mean for man. This is right in the way, of course. This is the distribution of differences. No, this is the distribution of averages for 20 men. And this is the distribution of average heights for 20 women, or for 10 women. And I want to find the distribution of differences sample means, right? So this is the distribution of sample means for men, and this is the distribution of sample means for women. So the distribution of differences of sample means is that same thing that we just did, combining normal distributions, because these are both normal distributions, but just with these distributions. So what I'm going to, so that's going to be called X bar M minus X bar W is normally distributed with a mean of, I guess I'll write it all here. So mu sub X bar M minus mu sub X bar W. I hope it's clear what that means. But if it's not, what I mean is the mean of the sampling distribution of X bar M, which is 69.5. And this is the mean of the sampling distribution of X bar W, which is 64.3. And I'm sorry, my handwriting is so terrible, you can't read it here, but this is an M and a W. Comma, the standard deviation, or excuse me, the square root of the standard deviation of the sampling distribution of X bar M, which is 2.5 over root. Oh no, sorry, that's not what I wanted. Sorry, let me back up here. So the 2.5 was sigma sub M over the square root of n sub M. Right, so it's the standard deviation of the population of the distribution of men, or a distribution of men's heights, divided by the square root of the sample size that we took from the men. And we're squaring that, just like we did before, plus this, sigma sub n, no, sigma sub w, I mean, over the square root of NW, NW. Squared, almost forgot the square. So that is, so I'm going to simplify this a little bit. So this is n normal distribution of mu sub X bar M minus mu sub X bar W, comma, portrait is in, it's just in the middle of everything. No matter where I'm going, it's right there, guys. So I'm over here. So the square root of these things squared and added together. So I'm just going to square those things individually. So this is the square root of sigma squared, sigma m squared over, when I square the square root, right? So I've got this square root of n sub m right here, and then I'm going to square it. That just gives me n sub m. N sub m plus sigma w squared over nw. No square root. Like so. This is the formula for the difference of two sampling distributions that where the central limit theorem applies. I hope that's clear that we need the central limit theorem to get all this. So let's calculate that. So this sigma m over square root nm was 0.56. And we're going to square that. So what I'm going to do here is I'm just going to subtract here, which this first bit is easy, right? This is the same thing as it was before. Mu sub x m bar is the same thing as mu sub m, and mu sub xw bar is the same thing as mu sub w, right? Just central limit theorem tells us that. So this number is still 5.2. 5.2. And then this square rooted thing over here, I'm just going to go over to the calculator and find that. It's just going to be 0.56 squared plus 0.76 squared, all square rooted. So let's go do that. now my picture's in the way over here. All right, we'll put it up here. No, I'm just going to have to move it when we get back. Actually, here, let me be more accurate by doing this squared plus this squared. So we had 0.943. 0.943. Okay, so all I did was exactly the same stuff I did for the other combined normal distributions. These happen to be sampling distributions to start, but that's irrelevant, right? They're still normal distributions, so we combine them just like we combined distributions over here, right? When I found these, you take you take their means, subtract them, you take their standard deviations, square them and add, and take the square root, and you get what we got. I don't know where I was going with that sentence, but that's what you end up with. So is that what I did here? Find the distribution of differences of sample means. Okay, so it's this. Notice that they're just numbers, right? 0.5 or 5.2, 0.943. So mean of 5.2, standard deviation of 0.943. Find the probability that the average height of a random sample of 20 American men is at least 7 inches greater than the average height of a random sample of 10 American women. So, of course, that's the same sample sizes that we've got. And so that is what this distribution is telling us. This is the distribution of all the possible differences of sample means of 20 American men's heights minus 10 American women's heights. That's what this is the distribution of. So let's go use it. 5.2, 0.943. Okay, so we've got, I can say that x bar m minus x bar w is approximately normally distributed with a mean of not 0, 5.2, and a standard deviation of 0.943. I'm uncertain about that 4. I'm going to go back and look. All right, success. I remembered a single number correctly. So I want to know what's the probability that one particular sample of 20 men, so that's x bar, and I hope it's clear that that's a lowercase x bar m minus x bar w. So this is the probability that x bar m minus x bar w is at least 7, greater than or equal to 7, right? So that's the thing that I asked about. So all we have to do is use this distribution right here. So I'm going to do 7 to infinity in this distribution. That's it. So the actual normal CDF stuff is really simple. It's determining what distribution you've got, right? So 0.943. Okay, so we've got second distributions, normal CDF, 7 to infinity, mean of 5.2, standard deviation of 0.943, based. So much smaller, right? 2.8% rather than the 30% it was before, which I'll explain why it's so much smaller in just a second. Let's write this down. So 2.8%, about equal to 2.8%. Okay, here's why that's smaller than it was over here when we were just talking about one man and one woman. Right, when we found probability that m minus w was greater than 7, and we got like 30%, right? So the thing you want to see is that distribution is centered at 5.2. All right, so let's compare these two distributions. So here is m minus w. I'm going to graph them roughly. M minus w is something that looks like this. It is relatively spread out. So this is 5.2, 5.2, and we've got, this is n 5.2. That's an interesting looking n I've got there. 3.466. And so x bar m minus x bar w, we figured out it was normally distributed with a mean of 5.2 and a standard deviation of 0.943, which is to say about a third of the standard deviation of this, which means it's going to be 3 times less spread out, which is to say that it'll be more compact, and 3 times taller, because the area under the whole thing is still 100%. So if you squish it in, it grows up because it has to have the same area. So what you end up with is something that looks like this. Sorry, this is not going to be to scale, but you get something that's much more concentrated around the mean, just as we've seen with standard deviation in the past. And so 7 was, over here somewhere, right? So this was like 30%. It's closer than that. So 7 was like here. So this is 30% over here, 30.2%. And 7 is like here. So this is 2.8%. Right? You can see that the area is much smaller under the bottom one because it's significantly taller and skinnier. I know it doesn't look taller because I didn't graph it taller, but picture it being stretched out taller as it should be. Like the tails are much shorter, and so that area to the right of 7 is significantly smaller when the standard deviation is smaller. So by the way, I could have made this so that this one would have been, this one would have been much bigger by including an area around the mean, right? If I'd said, what's the probability that the men are between 5 and 6 inches taller than the women, right? So then that would include like 5 to 6. And down here, that would include 5 to 6. And the bottom one would be much bigger because that's taller, right? That's a lot taller. And so basically, if you include an area away from the mean, shrinking the standard deviation causes the area to go down. If you include an area including the mean, shrinking the standard deviation will cause the area to go up, just because of what happens to the distributions. In fact, I'm going to pause my recording for just a second and go wump up my Desmos thing just so I can show you. All right, great. I've got my Desmos thing set up. Let me show you what these actually look like rather than my terrible sketching. So this is the normal distribution with a mean of 5.2. You can see that right here, and a standard deviation of 3.466. So I have another one graphed, which is the same thing, but the standard deviation is 0.943. Did it? No, I don't. No, that's not. What the heck? Why did it? 0.943. There. No, show it. Oh, sorry. There we go. That's what it looks like. So you can see that if I shaded in from 7 and up, right? So if I shade to the right from, I want this to be 7, right? You can see that we're going to get a lot of area under the one with a high standard deviation, and a relatively small area under the one with the low standard, or with the lower standard deviation that's taller, right? So that's what I've been trying to say here. And if I had gone from 5 to 6, let's see here. So if I go shade between, do that. If I'd gone from 5 to 6, right? So this would be, let's call this 6 here. If I do something that includes the middle, you can see here. So something like that, right? So 5 to 6, close enough. So you can see that I get only a relatively small area here, but if I continue this up, I would get a much larger area in the one with the smaller standard deviation because more of the data is around the mean. So that's why the difference in the two. And in general, when you squish the standard, when you make the standard deviation smaller, what you're doing is you're squishing the distribution, which pushes it up, right? You can see that the areas have to be the same because it's still a probability distribution with total area of 1. So I'll go back here for a second. Yeah, I think that's the last thing I wanted to say. Let me just quickly check and make sure that I've hit everything I wanted to, answer all the questions. Yes, that's really what I wanted to say. And so all the stuff that I've been showing you is going to go in the background, and I'll show you how the formulas are made. And we won't use them directly. We're gonna hit the buttons basically on the calculator, but I don't want to get in the habit of just hitting the buttons without understanding, and this is where the understanding comes from. So yeah, I don't think I need to sum up too well. I guess maybe I'll sum up a little bit, right? So here's how you combine two normal distributions, right? If A has this mean and standard deviation and B has that mean and standard deviation, then A minus B has this mean and standard deviation here. And you can do that with just regular all normal distributions. And you can also do that with sampling distributions, which is what we're actually going to be doing, because central limit theorem tells us that those sampling distributions are normal distributions. So you just treat them like any normal distributions when you want to combine them. That is actually the last thing I want to say. I'll go ahead and stop the video here, and I will see you guys in the next video.